Hello and welcome to the lecture 7 of EC 3030. So in this class we will be introducing the concept of transistors, more specifically MOSFETs, metal oxide semiconductor field effect transistors. So again I'm showing this cross-sectional image of an Intel 14 nanometer node chip that was rolled out in 2014 in the Intel Broadwell technology, and here we have so far talked about metals and also to an extent semiconductors, and these are the transistor here right at the bottom, and this is what an advanced node transistors looks like. So we will talk in details about these transistors. So right now we'll just introduce the concept of these devices. All right, so again one of the slides that we have previously shown. So in the integrated circuits we have three kinds of materials: metals, oxides and semiconductors. And for MOSFETs, we need all three of these material systems, including both N-type and P-type materials, N-type and P-type semiconductors. All right, so this is the structure of a MOSFET or a MOS capacitor. So on the left, there is a MOS capacitor, and on the right, there is a MOSFET or MOS transistors. So let's first look at a MOS capacitor. So it's a MOS capacitor, so it has a two terminals only, and we need to understand first a MOS capacitor to understand how a MOSFET works. So we have first a metal here, and here we have an oxide material, silicon dioxide in this specific example, and then we have a semiconductor. So we have a metal oxide semiconductor, and that's where this name comes from, metal oxide semiconductor or MOS. Now this is a two-terminal capacitor structure. On the other hand, in a MOSFET or MOS transistor, you have the gate oxide, metal, then this oxide, and then the semiconductor, and then you have two regions on the two sides of the system. So this semiconductor here, which we call the body, is doped P type in this case, and if so, this is what we call the body, and if this is P type, then these regions here are opposite type, N type, or here we are saying it's N plus, meaning that it is very highly doped with donors, and these two terminals are called source and drain. So here we call it the drain, and here this terminal is called source, and here this region, the interface between silicon dioxide and the semiconductor, this is the channel, and this metal is called the gate. Now the voltage that we apply at the gate is called the gate voltage, and then we apply a voltage here at the drain, which is called the drain voltage. And what we do is that by using this gate voltage, we control the amount of current that flows between the drain and source in a MOSFET. Okay, so let's introduce MOSFET as a switch. So for the purpose of this class, we will treat MOSFET as a switch. So by switch, the simplest possible example of switch is this one here, where we all use switches a lot. All right, so the basic function of switch, so if it's in zero position and there are this voltage here, if it's in zero position, then it's an open circuit, so there is no current flow and this appliance will not work. And if it's in the one position, then it will be a short, basically a very small resistance, and then a current will flow and this bulb will light up. Essentially, MOSFET, with a MOSFET, we want to do the same thing here, just that whether it's open, this the between these two terminal, the drain and source, whether this between these two terminal there is a high resistance or a low resistance or short, will be determined by the gate voltage. So that's all we want to do. So if the gate voltage here is very small, then it will be an open circuit, so there will not be any current flowing through. And if this voltage is larger than a certain voltage, which we call the threshold voltage, then the resistance between the drain and source will be very small, and then a current will flow and this bulb will light up. All right, so again this figure here, so I'll just say the same thing as we said in the previous slide, and we'll just want to talk a little bit more about the concept of threshold voltage. All right, so as we have said, so if say Vg equals to 0, then this will be an open circuit, so this circuit will look like this, and it is connected to positive and negative here, so it's open here. So there will be the current that flows through the circuit here will be 0. On the other hand, what we are saying here is that if the gate voltage is larger than a certain voltage, which we call the threshold voltage, then what we are saying is that the resistance here will be very small, and as such there will be a lot of current that will be flowing to the circuit. So usually what we do is that we draw the desired characteristics of a switch or the characteristics of an ideal switch. So the way we do it is that we say that, okay, so this is the drain and source terminal, and this is the current that is flowing through the transistor channel, and this is the gate voltage. So we plot the drain voltage drain current ID as a function of Vg, and this is the threshold voltage. And what we say is that the characteristics of the transistor should look like this. When the gate voltage is below threshold voltage, the current should be 0, and above threshold voltage the current should jump to another high value. So that's the behavior that's the desired behavior of a MOSFET or the behavior of an ideal switch. So in this class we will see that for a MOSFET, how does these characteristics look like for a MOSFET, and we'll also try to see how we can improve the behavior of a MOSFET so that it becomes very close to that of an ideal switch. So one of my favorite analogies for MOSFET is that of a water faucet. So let me quickly go over the concept. So here we have a water faucet, and you can think of this as the gate. So this is the gate valve you can consider, and this is the source, and say this is the drain. Now in a faucet you open the valve and then you get water coming from the source all the way to the drain. Alright, and the flow you can control with the gate. Now a MOSFET essentially does the same thing. By changing the gate voltage, you change the amount of current that flows through the channel. You can completely turn that flow of current as well. So the analogy that I want to give is that on the source side, say you have a reservoir. So this is the source, and say you have a drain here which does not have any water, and there is a barrier between them. Now the barrier is higher than the level of water here, so there won't be any flow of water from source or to the drain. But now if you open the valve, then what will happen is that the barrier will decrease. So let me try to use another color. So now let's say you have reduced the height of this barrier to this, and then you will get water flowing from the source to the drain. Now if you reduce the barrier further, you will have more and more water flowing from source to the drain, to the faucet. So this is an analogy, and this analogy we call the barrier model. So barrier model, and this barrier model is a popular model of explaining the operation of transistors, so which we will also look at the end of the section of the topic of transistors in a later lecture. Alright, so this is how a transistor looks like. So this is a 3D image of a 3D schematic image of a transistor, schematic diagram of a transistor. So here you have the drain, you have the source, this is the oxide, and this is the gate. So you apply a gate voltage here and a drain voltage here, and the source voltage is here. Now if this region, the yellow region, which is the channel, if it's p-type, then the drain will be n plus, meaning that it will be very highly doped with a donor. Now there are a bunch of quantities that define the transistor. The first one is the thickness of the oxide, which say we call Tox. Then the distance between the source and the drain, or this distance here. So this is what we call the channel length, or also this is equal to the length of the gate, so which also call it gate length or channel length. And then the other one is the width of the transistor, which is this dimension here, which we call W. Alright, so this is a 3-terminal device. So this is the typical symbol that we use for transistor. So this is the gate, and this two vertical lines, this represent the oxide here. So this is this region, and then you have the drain and the source, and this is a 2D version of the same MOSFET here. All right. Okay, so let me end this lecture with introducing a simple barrier model of a MOSFET. So what we draw is that we, from the source to the drain, we say that there is a barrier to current flow. And so right now this is, say, Vg is equals to 0, so it's smaller than threshold voltage, and the barrier is high enough that no charge carrier can flow from the source to drain. Now if we increase the gate voltage, what this will essentially do is that it will reduce the barrier height from the source to drain, and say this is for Vg1 larger than Vg, which is 0, and when the voltage is larger than threshold voltage, when this is Vg2, which is larger than threshold voltage, then the barrier is small enough, the substantial amount of current can start flowing from the source to drain. So essentially what the barrier model tells is that by using the gate voltage, we can change the barrier for the charge carriers to flow from the source and drain, and as a result, by changing the gate voltage, we can control the current that flows through the channel between the drain and source. Alright,